Hey, welcome! Today, we are diving deep into kinematics, which is really just the art of describing motion. We're going to build a kind of visual toolkit that lets us see the hidden geometry behind pretty much any object's journey. So, just think about that for a second. Every single trip you take, a ball you might throw, or even a car just driving by, what if its entire story, I'm talking its speed, its direction, all the stops and starts, could be perfectly captured and understood with just a simple line on a graph? Well, guess what? It can. And today, we're going to learn exactly how to read that story. Okay, first things first. Before we can tell any story, you've got to know the words, right? So we need to assemble the basic parts, the vocabulary of motion. So in physics, you've basically got two main types of measurements. Over on the left, you have scalars. These just have a magnitude or a size. Think about a car's speedometer. It says 60 miles per hour. That's a scalar. But on the right, you have vectors. Now, these are a bit more specific. They have both a magnitude and a direction. So instead of just the car's speed, we talk about its velocity, 60 miles per hour, heading north. That direction, that's the crucial little piece of info that makes it a vector. For our toolkit, we're really just going to focus on three core metrics. We've got the scalar quantity of time, which we measure in seconds, and then we've got two key vectors: velocity, which is just how fast your position is changing, and acceleration, which is how fast your velocity is changing. And you know that weird unit for acceleration, meters per second squared? All that really means is how many meters per second is my velocity changing every single second? These three are the building blocks for just about any kind of motion you can imagine. All right, so we've got the vocabulary down. Now for this secret weapon, the blueprint that translates all this physics of motion into a language we can read in an instant: the graph. You're looking at our Rosetta Stone for motion. This chart shows us that the shape of a line tells a story. It's really simple. A flat horizontal line, that always means constant. So on a displacement graph, a flat line means your position is constant. You're not moving. But see that same flat line on a velocity graph? That means you have a constant velocity. You're moving at a perfectly steady speed. The second that line starts to slope, you know something is changing. And that brings us to the most important point. The slope of the line tells you how fast something is changing. It's that simple. On a displacement time graph, the slope is the velocity. A really steep line means a high velocity. And, you guessed it, on a velocity time graph, the slope is the acceleration. This one single idea, that the slope is the rate of change, that is the first master key to our entire toolkit. But what if we want to go the other way? I mean, we know how to find velocity and acceleration from a graph, but how do we figure out the total distance an object has traveled? Well, for that, we need the second key to our toolkit. And this illustrates our second tool perfectly: area. It turns out, if you look at the area under a velocity time graph, you are literally looking at the total displacement. You can see it here, broken down into two simple shapes. The rectangle on the bottom, that's the distance the object would have gone if it never accelerated. And that triangle on top, that's the extra distance it covered because it was accelerating. Just find the area of those shapes, add them up, and you know exactly how far it went. Okay, so now we have our two master tools: slope for the rate of change and area for the total displacement. Now let's put this toolkit to work and see what kinds of stories we can uncover in a few real-world examples. Let's start with something simple: a car hitting the brakes. Okay, so for the first 10 seconds, you can see the velocity graph is just a flat line. It's cruising along at a constant 12 meters per second. Then bam, the driver slams on the brakes. The line slopes down, showing us a negative acceleration, or what we call deceleration. And if we want to know how far the car traveled while it was braking, we just calculate the area of that shaded triangle. The whole story of that stop is right there in the graph. Now let's look at something a little more complex. This is a displacement time graph of a bicycle commute, and you can see the whole narrative. First, there's a steady ride away from home. That's the positive slope. Then, a short break where the line goes flat. No change in position. After the break, the cyclist keeps going, before finally turning around and heading back home, which is shown by that steep, negative slope. It's a full story, all told with a single line. And what's so amazing about this is that these rules are universal. They even describe gravity perfectly. When an object is in free fall, its velocity increases by the same amount every single second. It's about 10 meters per second. On a velocity time graph, that creates a perfect straight sloped line. This geometry of motion is literally everywhere you look. So let's pull all this together. We've talked about slope, we've talked about area, and we've seen them in action. Let's take a look at the complete master toolkit. And there it is. This is the whole thing. the unifying framework for one-dimensional motion. And it's this really beautiful cyclical relationship. If you start with a displacement graph, you find the slope to get velocity. Find the slope of that graph, and you get acceleration. And what if you want to go backwards? Well, if you have an acceleration graph, the area underneath gives you the change in velocity. And the area under the velocity graph, that gives you the displacement. It's all connected. Slope takes you down, area brings you back up. So there you have it. You have the blueprint. You have the language to decode the movement that's happening all around you every single day. You can see the story of a journey not just as something happening in the world, but as a geometric shape on a page. So the real question is, now that you can read the story of motion, what stories are you going to find?